All right, welcome back to Computer Vision Unlocked, where we try to cover what's really happening with AI and synthetic data. There's so many tools and so much changing in this field that it's almost impossible to actually keep up. And so we've stopped trying. Instead of trying to keep up, what we like to do is take a chance to just actually talk to some of the engineers who are on the front lines. And so today we get to talk with Michael Blazej, one of our top engineers at Rendered.ai, who's been leading a lot of our simulation work, especially around synthetic aperture radar. Michael, can you say hi?
Hey, yeah, my name is Michael Blazej. I'm glad to be here.
Awesome to have you. So Mike, we've been working together a lot on SAR. Do you want to share a little bit on why you find SAR to be interesting and important?
I find SAR to be interesting and rather simulation mostly, but SAR in particular, because of how much information you can extract from it. Um, with not independent of environmental factors, day or night. Uh, you know, different platforms do different things,
Absolutely.
and
So, we can
and
see through clouds, we can see at night. We're not reliant on illumination from different sources, which also means that our illumination doesn't change all the time.
right, and the amount of signal processing you can direct towards the resulting data allows you to extract a vast amount of information from what you record, which I find very interesting.
So hugely powerful tool, but difficult to actually build AI tools around because it's hard to get data and it's hard to label data.
That's true. SAR images don't look like normal data. A large building doesn't look like it would in a visual image, and it also dependent on where the sensor is relative to the scene itself. So, yeah,
And so at Rendered, right, we've been working on producing synthetics to replace that. And it's been tough to find the right simulator. So we decided to roll our own and build some of our own simulation technologies. Can you tell us a little bit about what that journey has been like for you?
yeah. So I've been working with simulators for just over 7 years now, and so my first experience was with a proprietary one at a previous employer, and it was fantastic. It's great, but it's not, it's not publicly available, and there are a few that are, and the few that are, um, some are not easily accessible, and some are just, not designed for high speed data generation. And so that's really why we decided to go our own path.
Yeah, high speed and high quality, right? Like you have to have accuracy and you have to be able to produce enough data to actually train on.
Right.
So you dove in and looked, I mean, you did this at Rendered, like looked at a lot of different options for being able to do that and what sorts of engines to build our simulator on top of. And where did that lead you?
It's true. I did. It led me to the OptiX ray tracer from NVIDIA. It's something I heard about 7 years ago, and that was when I was really digging into CUDA at the time. So really, they're NVIDIA's core technology for writing kernels on top of their hardware. And OptiX is really one level above that, where they take care of all the hard ray tracing part, boundary value hierarchy, and all the ray tracing guts.
Yeah.
And they really expose an interface that's actually quite, I mean, now I could say simple to use, um, that we can use to build a really high quality SAR simulator, which is what we've got today.
Yeah, awesome. So the BVH trees and everything for those who care. I don't think I even knew what BVH meant until you just said that. Heard
Yeah.
the term used so often. Um, and so, how difficult was it to actually leverage optics?
They actually, I mean, I do have a significant amount of experience in C++ and CUDA, and so it wasn't that hard because they provided an SDK that has 20 or 30 examples in it. I found one of the examples that I've actually seen used in a couple other projects, and I just started to expand off of that and build off of that. And I was able to build a multi-bounce system that was able to place a scatterer in the proper range and Doppler bin, which was really interesting. And I think I shared that with you, and that's when we kind of turned this into a company project.
Exactly, exactly. And then share a little bit about the results, because I know the speed and accuracy has been pretty amazing.
The speed and accuracy has been really fun. We have configuration parameters that have allowed us to really turn up the fidelity or turn up the speed. And so I've had experience building a 1 kilometer scene of Ukraine that we've shared with a couple of customers. And on our highest fidelity setting, that took about 10 hours to run on an L40S. I've just turned down the fidelity a little bit, and now I can get it to run on 30 minutes on the same hardware.
All right.
And the images are looking quite good.
And
So
just for those of you watching at home, that simulation, which is a multi-kilometer scene, probably on a typical simulation stack would be days, if not weeks, to simulate. I mean, it's a huge amount of environment that needs to be simulated.
it is a significant environment. We are sampling at on the order of a wavelength, which is very fine.
Which is about 3 centimeters, guys. For those watching at home, we have to model waves interacting every 3 centimeters or less across multiple kilometers, and then you got to do that, tens of thousands of times for every radar impulse to produce these images. So it's a huge, huge simulation effort. But
That's correct.
exciting.
That's correct. So I was going to say, for scenes like that, we are regularly casting many billions of rays, and so you can kind of get an idea of what level of compute is required to generate these kind of images.
So exciting. And to do it for something that's so meaningful, right? Actually helping us to understand like essentially our world, and how we can image it and get to know it better, track it better.
That's right.
Awesome. Well, thanks for taking time with us. Good talking to you, Michael.
It's good talking to you too.
All right. Take care.